Thank you for the introduction, and thanks for having me, and also for the other presentations. It was really nice to also listen to other presentations from different topics, and this will be a bit different, although it's also of relevance to the first presentation from Ericsson, but here, so I would like to focus maybe more on what, from at least from our perspective, on what can AI bring to future mobile networks, and particularly maybe as we move towards 6G networks. So I am Mohammed Elbamby from Nokia Bell Labs, and so Nokia Bell Labs currently is the research labs belonging to Nokia, and it's we work at different maybe fields related to technology and telecommunication networks. And where I work, we work on AI for network automation and for enabling the networks to serve different use cases and applications in the future. So when we speak about AI for networks, there are different aspects, and it's a big topic, and many of them are also related to what's within the network and the communication link, which some of them also will be covered in other talks today, for example, from Anis. But what I would like to talk about here is more from the use case and application perspective, like how we see AI bringing enabling networks to serve different applications and different use cases in the future as we move from 5G networks towards 6G or beyond 5G networks. So that's what how we look at 6G as compared to existing or previous generations. So if we look at it in an abstract way, that 2G and 3G started by what we call unleashing this potential of human connections and mobility. So we wanted just to give connectivity to users or to humans who are moving around. Basically, connectivity, it was like calls, text, and then maybe there was this limited data connections in 3G for like simple tasks. 4G focused more on this information and social interaction and started to provide this media, what we call media or mobile broadband, or you can basically stream videos and many applications that are around videos. And it was mainly focusing on high data rates. 5G started to look more at machines and sensors and started to see how can we provide these different types of connectivity that's not just about the high data rate, but how we can provide guarantees, how we can provide reliability, how the low latency applications that are sensitive to us, so we need to use it always. We still don't feel like connecting it wirelessly, so we still use the wires as with use cases that are in the factory and industrial automation, and 5G is starting to tap into these use cases. 6G will start to continue along this direction, but as we see it, we see as it's bringing this third dimension, which is the human dimension, in addition to the physical and digital world. So we hear a lot about the metaverse and VR. Maybe we always hear about it in the context of consumer metaverse and VR, and whether this will be a mainstream or not, maybe we don't know yet. But when you look at the immersive applications or the applications that involve the human sensor beyond the physical and digital domains, it also includes a digital twin. It includes the processes in the factories. It includes knowing, understanding the processes that are beyond what you see, for example, in a physical factory or in an industrial site, or in even entertainment or playing like gaming arcade or something, like you see in front of you, like the physical world, and then there is the human aspects, and then there is the virtual worlds that's beyond this. So connecting the experiences and how these experiences are perceived in these three domains is what we see as 6G will be able to tap into, or have the potential to provide services towards this direction. So if you look in more detail, what kind of use cases we see that as we evolve towards 6G. So from 5G that provides high quality video and aims for this beyond 4K video streaming and object driven, let's say digital twinning, like if you want a digital twin or a digital replica of a process or of a machine, and also related to this data communication and control. 5G moves towards more of this fully immersive or XR or like extended reality in general, including virtual reality and augmented reality. What's there is usually higher data rate than 4K videos and so on, and also more low latency needs. Then also when we say vertical application, like for example, this large scale digital construction, for example, these vertical farms and so on, this is one of the use cases where also we believe that 5G in the future will be covering. And then also this beyond communication, which we see that networks providing other services, including, for example, location and positioning. So that's beyond the outdoor positioning and localization that's usually based on GPS and so on. But if you need very accurate and precise localization also within indoor scenarios, as with, for example, robots in a factory, then this is something that networks are able to, or at least future networks will be able to provide using sensors related to wireless signal. 6G looks at more applications that are beyond this. So what we say holographic transmission is maybe this is an extension of the XR or VR, in which you want a very high quality and precise representation, for example, of humans who are communicating and want to like telepresence and use cases where that includes very complex processing and computation, in addition to very high data rate communication that you would need there. It needs a combination of it needs data that's collected reliably from a large combination of sensors, and that includes several stages that need to be performed successfully so that we can achieve services like this. And then also when we look at digital twins that are beyond a single object, but let's say how to keep a real-time synchronous digital twin of a factory or even of a smart city. And then something more about this intent-based autonomy, which we will talk about in a bit in more detail, which is how to understand the intents of an application, of a user, of a human, and how to execute something at the network in return. This also relates to the NLP discussion, although what we are looking at now is still in machine language. But then the natural extension to this would be how to also understand, from human let's say prompts or human sentence, what do you want really the application or the network to do to your application. And when you look now at the networks, so we were looking at the use case, but the network itself, when it starts to serve use cases like this, we are moving from this one-size-fits-all network to specialized networks that are embedded into machines, into vehicles, into humans, also related to the body networks in for example, pacemaker, or in different medical devices in smart homes or houses. Those are also, this is from the hardware point of view where the networks are, and also from the requirements that are and the capabilities that these devices are able to provide, which include many different capabilities that are not maybe in today's network. And when you look from the AI perspective, the requirements starting from the hardware and the capability of the device until the management of the network and the automation, the requirements span all these domains and need to all be working together towards realizing these use cases. If you look more into this, what we like, some of these examples we mentioned here, and what we see the requirements are. So if we look at 3 use cases here in vehicle, in body, or in production control. So those are maybe some of the requirements that networks aim to provide today, or starting from 5G. So until before 5G, networks were best efforts. So you just try to provide as much capacity or data rates as you can, but there are requirements like latency, jitter, and then the service availability, and then also the localization accuracy if you are looking at this. So these 3 different use cases here, you will see that they have these different requirements envelope, and the ability to provide all of these, and sometimes at the same time. And if they coexist physically at the same time, how can you really optimize the resources, the wireless resources, the computing, the cloud, the processing, all of these together towards providing this kind of you basically partition the network into different components that needs, each component is isolated in a way that it needs to provide this service to this, let's say, to a body network, to a vehicle network, to a production control network, and at the same time that without like just using redundant resources, but how to be smart about the resources that you have so that you can serve all of these without having the cost getting out of control. So if you look at this, so this is also to show that requirements go beyond data rates and latency towards how the user is experiencing, for example, the service in terms of data rate and other quality of services that they have. What's the energy efficiency of a network? What is the connection density, for example, when you are connecting a network, and this reliability and localization and so on. And if you see the use cases that we expect to be covering are falling like at different places within this envelope of requirements or the capabilities that we can provide. So let's look at two maybe use cases that, for example, what can this network what the network can provide, and what's the AI or machine learning role here. So if we look at this kind of immersive experience within an entertainment event or a sport event in a stadium, so users have their, for example, the glasses which show something that's augmented on top of what they see in the event. And there are cameras that film the event and enable them to show, for example, replays or data augmented on what they watch. First, a network like this cannot stream the video to a remote server and then just send it back to the user or processing, because they can't see and hear in real time. You need an edge server there in the site that processes this and send them back, for example, what they have to see. Using this processing, providing this processing at low latency, and also providing the computation at low latency is something that needs AI at different aspects of this. Predicting where the users are looking at, for example, this field of view prediction, and sending them only what they see in front of them, not the whole frame, is something in VR aspects that's needed, and that's very important to the network, so you don't have to stream much more data than what the users really need. But this is one example. But if we look more into the industrial and factory use cases, which is something that we believe is becomes more and more important, and more relying on good connectivity and networks that are more understanding of what's the application that's using it, rather than being a data pipe. So if you look at the use cases of robots moving around factories, and cameras that are also taking videos of what's in the factory, and based on that we do analytics and we do processing of the tasks that's going on in the factory, plus also controlling the robots that are if they are automated or automatically controlled by a server that's connected wirelessly to the robots. Because the idea here, why we want to have this over wireless, because we want to enable this like unlimited mobility of the robots around, and at the same time we provide them with all the capabilities that are in today's fixed robots that are connected with wires. So the AI roles here are at different stages of this, including starting from the video and sensory data analytics to the predictive decision making, which is something that's of high importance at the network side. For example, can you predict where the robot is heading to? Can you predict the process pattern, what's happening there? And then you start to assign the wireless resources in advance, so that you can actually enable the networks to be able to be proactive and satisfy these services in advance. But this is more about context awareness, which you can see also exists, or there were works that were looking at this from even 5G networks. But what we want to look at more here, and quickly, because I have a few minutes, that we are looking at AI understanding what you say the business goal or the intent of different applications using the network. So when you say specialized networks that serve different applications and know exactly what they want, then you need to understand the intent. The application will not tell you, I want to configure this network this way and that network and this router and this base station, because the application is not expected to understand much about the network. The other thing is if they speak in their language, Like you say, for example, I want the VR quality to be that much. I don't want the virtual reality users to get motion sickness because there is a latency, but maybe the application does not understand much the mapping between this and that. So they want to speak their own language, and then you want to understand and the network how to understand the intent of the applications and realize it. So how to satisfy each application requirements using this intent-based management? How can you infer the application goal before it's actually sent to the network, and to provision the right capabilities at the network to satisfy that goal? This is quickly from one example of a study that we looked at it in an industrial scenario. So that scenario is a bit complex, in which you have two different types of services that you try to serve at the same time. So remotely controlled robots, so they are wirelessly controlled by users, humans, who move with the robots towards machines to start to perform something with the machines that are the fixed machines. These fixed machines, when the robots start to interact with it, it does a task that needs also data that's downloaded from the server wirelessly. This is a high data rate, but maybe it's not a control rate, doesn't need much reliability, but the robot control needs much reliability, or otherwise if you send a short packet with an error, then it causes like a error of high cost if you cannot control the moving robots correctly. So what we were doing is, can you understand what the application, or predict what's the intent of the application before it's being told? Like, can you predict from the data about the movements of the robots where they are going to be next? And then you predict what's the task they are going to be next, because you see where is the nearest machine where they are heading to. In that case, you start to already process the task of this machine, send it to it, and then you save more resources when the robot actually arrives there. So that's the approach: predict the robot route, and then based on that, predict actually what that robot wants to do, and then optimize that. One thing here is, we don't optimize only what's the robot is going, like when we know, for example, what task is going to be in the machine, that's one application. We optimized how the network served two different applications, the robot control and the machine processing, or the task that's actually happening in the factory, based on what we predict from one application. And that's one other thing, which is that today's network deal with every session individually, but can you actually get the knowledge from one application and use it in another application? You need also, of course, to understand the coupling between these different applications. Maybe this is quick results that I just wanted to show, but quickly, that we saw that, for example, this prediction horizon, like when you try to predict how much in advance, how many seconds, for example, in advance of the before the robot arrives at the machine, which task is going to be doing. So if you predict and start to take action about a very short time, you usually have a good accuracy, but you still don't have much time to really send the data quickly. So you have the right prediction, but you don't have much time to actually do something proactively to make the network work better, so that you minimize, for example, this robot waiting time when it arrives there. As you have a better prediction, but you still have time to react, then this is the best gain that we get. But if you start to predict well in advance, you have time to proactively take a decision, but the problem is your accuracy is not accurate anymore, because you try to predict like earlier time. This is a common like phenomena that you see with this, when you try to predict something and take action based on it. But usually there is this like sweet spot where you try to predict something in advance, but not very well in advance. This is also results that compare, for example, how the control packets were reliably sent to the robots when we use this, when we introduce this reliability that's based on predicting what the robot will be doing, and then saving resources to serve the robots in advance based on that. Maybe this is, so we just, maybe if I conclude like that, we see potential here in providing insights about the applications and machine goals to the network, so that the networks are understanding really what's being used, and how it's being used, and potential also to use this across applications and provide more application awareness to networks. One question that comes next is, can we actually incorporate the NLP tools to start to understand this based on human language? Can the network really get human, which we believe that the recent advances is a big step towards this in NLP and in understanding human language. So can we use human language to describe how we want the network to behave, translate this into network configuration, and automatically start to change the network configuration to serve this application requirement. And this is maybe the last question concludes then my talk here. So